So if you were at the Discovery Center at all in, I think, February, so before we closed, I was putting together these little like hands-on math um, activities / exhibits like by the back window of the Discovery Center. And this is actually based on an exhibit I did with the Pythagorean theorem. So you may have seen some of this stuff before if you visited the Discovery Center. But what we're gonna do is we're gonna talk about who Pythagoras was, why the theorem is named after him, what the theorem says, maybe remind ourselves if we remember from high school geometry, and then just go over some ways that it's been shown to be true. So let's get started. So right here, we see a picture of Pythagoras. So this is him as in Raphael's The School of Athens. So from this picture, and also probably from his name, you can deduce that he was an ancient Greek. He was a philosopher, but like all good ancient Greek academics, he was kind of a jack of all trades. So he made important developments in math, astronomy, music theory, just basically anything vaguely mathy. He's often called the first pure mathematician, which just means that he was looking at math as just kind of from a philosophical point of view, which makes sense because he was a philosopher, instead of thinking about it as a tool to do other sciences. A decent amount is known about his life, but it's kind of questionable about what is known because a lot of biographies were written about him, but in those biographies he's often presented as a godlike figure. So some historians treat it as kind of stories or legends instead of accurate information. And so I'm gonna kind of skip over his early life and get to the meat and potatoes of his math career. If you are interested in seeing about what his childhood and early adulthood was like, I'll have some resources at the end, just with some biographies about him and things like that. But in 525 BCE, he founded his school in southern Italy, which then was still a part of the Grecian Empire. And the school is called the Brotherhood of Pythagoreans, but both men and women were allowed to join it. And at that school, they were studying philosophy and religion through numbers. And so Pythagoras led the students in his belief. And so I'm just gonna go over like the 5 main parts of his teachings. So the first thing was, at its deepest level, reality is mathematical in nature, which is kind of something that we still think of today. Mathematicians think of math as the language of the universe. I mean, if you think about it, physics is describing what's happening, and you do physics by doing calculus. So that one's still something that's thought to be true. His next teaching was that philosophy can be used for spiritual purification, which is an interesting idea. The third is the soul can rise to union with the divine. Certain symbols have mystical significance. And then lastly, all brothers of the order should observe strict loyalty and secrecy. So as you can see, as we go through these beliefs, they get sort of farther away from what you would expect from a math school. And that's because it was a little less of a school and a little more of a cult. So the people in the inner circle of the Brotherhood of Pythagoreans, they had to live at the school, they had to give up all their possessions, they weren't allowed to eat meat anymore, and they had to be really, really loyal to Pythagoras and not talk to anybody about what they were doing at the school. People on the outer circle, they were allowed to come and go as they pleased, and go back to their homes with their things and eat meat if they wanted to, but they were still expected to be really loyal and secret about what they were doing. So because of this secrecy, there isn't really that much known about Pythagoras's work. And by that I mean, we know what the school did at this point, but we don't know what Pythagoras actually did and what his students did because they just attributed everything to him. So it's called the Pythagorean theorem because Pythagoras's name was on it at one point, but we don't actually know if that's because of him or because of his students. So what is the work they were doing at this school? They weren't trying to solve problems or discover new formulas or anything like that. Like I said, they were pure mathematicians. So they were just interested in the why of mathematics. They were studying the principles of it, the concepts of numbers and shapes and just abstract ideas, which is really similar to modern mathematics. So modern mathematicians, modern pure mathematicians, aren't just sitting and developing formulas all day. They're thinking about how numbers relate to each other and what patterns they can see and things like that. And so some of these things that they were thinking about numbers are similar to what we think about today. So they had ideas of even and odd numbers. They talked about triangular numbers and perfect numbers. And to go over what those are, so a triangular number is a number where if you have a number of dots, you can arrange them into a triangle. I have a little pen tool here. So 3, for example, is a triangular number because you could have 1, 2, 3 dots all arranged in a little triangle. 6 is also a triangular number because if we add another little row of dots, this pyramid, that's also a triangle. A perfect number is one whose proper divisors add up to that number. So a proper divisor is a number that divides a number, but isn't that exact number. So 6, 1, 2, 3 all divide 6, and then 1 plus 2 plus 3 equals 6. So that's a perfect number. Unlike today, they had some other ideas about numbers. So they thought that numbers had personalities. They thought numbers were masculine and feminine and beautiful and ugly, which are not really things we talk about numbers being like today. So a masculine number to the Pythagoreans was just an odd number. A feminine number was an even number. And then a masculine and a feminine number could get married, and then you have a marriage number. So 2 is feminine, 3 is masculine, 5 is their marriage number, things like that. Not what modern mathematicians think about numbers being like. But what we really associate Pythagoras with in the Brotherhood of Pythagoreans is the Pythagorean theorem, which is what we are all here to talk about tonight. But it's kind of funny because he probably wasn't even the first to notice or even prove this theorem. There's evidence that ancient Babylonians, ancient Indians, ancient Chinese, they all proved it before the Greeks were even thinking about it. And calling it the Pythagorean theorem isn't a commonality across the world. In China, for instance, they call it I'm going to say this wrong probably, the Gaoju theorem, which translates to straight line hypotenuse theorem. But now that we know a little bit about Pythagoras, why it's called the Pythagorean theorem, let's talk about what the theorem actually is. So maybe you remember this from high school geometry, maybe not. Let's just go over it so we're all on the same page. The Pythagorean theorem has to do with right triangles. So in a right triangle, you have a right angle, a 90-degree angle. So that's this guy right here. We call the sides adjacent to the 90-degree angle the legs of the triangle. Here, the shorter leg, we're calling it A, the longer one B, and then the side across from the right angle is called the hypotenuse. Here, we're calling it C. And so the Pythagorean theorem says if we take the square of the legs, add them together, we're going to get the square of the hypotenuse. Or in terms of how we denoted this triangle, a squared plus b squared equals c squared. And before we get into showing why this is true, let's just talk about why it is a theorem and what a theorem is. So a theorem is just a statement that's true, but the fact that it's true isn't really obvious. So looking at that triangle, it's perfectly believable that if we square the hypotenuse and square the sides and add them together, they might be equal. But that's not really an obvious thing about it. A theorem is usually a big statement, so a major result, but smaller results, you can also have smaller true statements, but we usually don't call them theorems. They're usually called corollaries or lemmas, depending on how they're related to the theorem. And what we need to do with a theorem is show that it's true. So in math, there are definitions and axioms and just rules that we have about things, theorems that have been proved before, and you can all use those to show that further things are true. And the way that we show things are true is with a proof in math. And that's just a series of true statements that follow each other in a logical way. And usually proofs are words. They're like little paragraphs written out that just use definitions and axioms and previously proved theorems. But tonight we're going to be focusing on a thing called the proof without words. And that's essentially just a picture that contains all the information that you need to show that the theorem or whatever you're talking about is true. Sometimes there's a little bit of text in it, but usually it's just an image, and it's kind of like a mathematical puzzle. And it's up to the reader to figure out all the information that the picture is giving, and to figure out why it's showing the theorem is true. So let's dive in. Let's prove the Pythagorean theorem in a few different ways. And we're going to be showing 5 different proofs for the Pythagorean theorem tonight. And after each one, I'm going to pause for questions. So if you have any questions at that point, feel free to write them in the chat, and I can go over anything that was a little confusing in the proof. Okay, so here is our first proof that we're going to look at. And what we have is 2 figures. So we have this one over here, which is a square, and then we have this one over here, a compound shape. And the thing to notice about these is that they are made up of the same smaller shapes. So there are 4 of these yellow triangles. Here are the 4 triangles, here are the 4 triangles, and then one of these blue squares. So essentially what we're doing here is we're taking the triangles and squares that we use to make this big square, we're rearranging them, and we're getting this guy over here. And being someone with a math background, the first thing I want to do when I see a picture is label it. So that's going to be our first step in working out what this proof is telling us. So I'm going to call the short leg of this triangle A, the long leg B, and the hypotenuse C, just like how we defined the theorem itself. And then I just threw all those labels all over all the triangles. So now we have a name for all the lengths of the triangles, but we don't have a name for the lengths of the square. But we can figure that out based on the information we have here. So this whole length right here is B, and this part of that length is A. So if we want to know what the side of the square is, it's just the whole length B without that little length A. So right there, it's going to be B minus A. And then we can put that label on the other square just to be clear that they're the same size. Okay, so at this point we have everything labeled. We have sizes in terms of letters, which is what we want for our proof. So now we want to think about what to do next. Now the Pythagorean theorem is talking about things in terms of squares. And 2-dimensional shapes have sort of 2 measurements that we use for them. So we have the perimeter, which is the length around the outside of the shape. And then we have the area, so the amount of space that it takes up. And the thing about area is it's measured in square units. So since it's square units, we want to be talking about square length. That's probably a good place to start. So let's find the area of these shapes. So for the yellow triangle, the area formula for a triangle is 1/2 the base of the triangle times the height. For this triangle, the base is A, the height is B, so the area is 1/2 A times B. For the square, the area of that is just length times width. The length and width are the same for a square, so it's just going to be B minus A times B minus A. And if we multiply those out together, we get B squared minus BA minus AB plus A squared. These are really just the same terms written in a different order. So we can simplify that to get B squared minus 2AB plus A squared. Okay, so now we have the area of the smaller shapes, but we were given these bigger shapes made up of those. So it seems like the logical next step would be to find the area of these bigger shapes now that we have the area of the smaller ones. So let's do that. So if we want to find the area of the square, this guy right here, remember we were just saying the area of a square is the product of its width and length. Here, the width and length of the square is C because that's the hypotenuse of the triangle. So the area of that square is C squared. We can find the area of this compound shape by using the additive property of area, and that's just a fancy way of saying we can add up the area of each of these shapes. So let's do that. So there are 4 triangles, So 4 times the area of the triangle plus the area of the square. That's just from the last slide. We can simplify that a little bit. So 4 times 1/2 gives us 2. So we have 2ab plus b squared minus 2ab plus a squared. But now we have the same term right there. We have a +1 and a -1, so those go away. And we're just left with b squared plus a squared. But the thing to remember is that these are made up of the same shapes. So if they're made up of the same shapes, they need to have the same area. So if they have the same area, then we have c squared equals a squared plus b squared, which is what we were trying to prove. So we're done. Yay! And so that is the end of proof 1. And at this point, I will pause. And if there are any questions, feel free to write those in the chat. And if not, I will move on to the next one.
Nothing so far. So.
Okay, cool. Great start. We're all understanding.
Oh, and Phyllis says neat. And I agree, because I was suddenly thinking, oh my gosh, I begin to understand all those things that my teachers were telling me that I never paid attention to. So.
Awesome. Okay, so proof number 2. So this one is kind of a similar idea to the first one. So we have 2 shapes. We have the first one is made up of 4 triangles, 4 copies of the same triangle, and a big pink square in the middle. And then the other one has those same 4 triangles, but now we have a small blue square and a medium-sized gray square. So similar setup. Let's start the same way. Let's start by labeling things. So again, we'll call the short leg of the triangle A, the long leg B, and the hypotenuse C, just to be consistent with what we've been doing. So what that says is that this pink square has side length C, this blue square has side length A, and this gray square has side length B. And again, we're doing a similar thing. So let's find the area of those. So the yellow triangle, the area is still going to be 1/2 AB. The blue square, side lengths A, so its area is A squared. The gray square, side lengths B, so its area is B squared. And the pink square, same idea, has an area of C squared. So since we have the area of the small shapes, let's find the area of the big shapes. So the first thing we want to notice here is that both of these squares, so this one with the big pink square in the middle and this one with the blue square and the gray square, both of these have side lengths of A plus B. And just to be clear on why that is, so this length of the triangle is B, that length's A, there's B, so the side lengths are A plus B. Here, this square has side length A, this triangle has side length B, so this side length is A plus B. Same idea over here. And if we were to check these, we know that this side length is A, that side length of the square is B. Same idea. So then the area of both of these squares is going to be those side lengths multiplied by each other. And if we multiply that all out, we get A squared plus 2AB plus B squared as the area for both of those squares. But we can also calculate the area using the additive property of area. So again, that's just a fancy way of saying we can add up the area of the small shapes that make the big shape. So the top square we'll call square 1, the bottom square 2. The area of square 1, it has 4 of those yellow triangles. They have an area of 1/2 AB, and it has 1 pink square with an area of C squared. So just to multiply that out, we get 2AB plus C squared as the area of that. For square 2, we have 4 of those yellow triangles, 1 blue square with an area of A squared, and 1 gray squared with an area of B squared. Multiply that out, we get 2AB plus A squared plus B squared. But the thing to remember is a shape can only have one area. So if we find the area in different ways, they all need to be equal. So square 1 has an area of 2AB plus C squared, but it also has this area, the A squared plus 2AB plus B squared. Same thing for square 2. And then if two things are equal to the same thing, by the transitive property, they have to be equal to each other. So 2ab plus c squared equals 2ab plus a squared plus b squared. We have a 2ab on both sides, so subtract it off. And there's our theorem. And again, we're done. Quick and easy, right? So since we've reached the end of proof 2, again, I'll take a quick pause. If there are any questions or anything was confusing in that one, feel free to ask.
Nothing so far.
Okay, cool. So the difference between this one and the first one, obviously they're set up a little bit differently, but the main idea of this first one is that it's kind of like the negative space is equal to each other. So the space that's missing, we can think about it as that pink square, and over here the space that's missing is the blue and gray square, as opposed to the first one where it was all just positive space, if that makes sense, a different way of thinking about it. Okay.
We do have one more comment that is just, Katie, you're making math fun.
Oh, good. It's more fun when there are pictures, right?
I agree. And comments. Comments help too.
Yeah. Okay, so now on to proof 3. So this one is our first one that's a little bit different. So this time we have 2 copies of this blue triangle, and then we have a third pink triangle. So again, we'll start by labeling our picture. So the blue triangle, that's the one we'll call the ABC triangle. So the short leg A, the long leg B, the hypotenuse C, just like how we define the theorem. And then for this pink triangle, the legs are C, but in the end, we're not going to need to know what the length of the hypotenuse is, so I'm not going to even bother labeling that guy. And what we should notice here is the shape that these triangles form. So this time we're not making a square or some wonky little compound shape. Instead, we have a trapezoid. So a trapezoid is just a shape that has at least 2 parallel sides. And that's what we have here. So these 2, we have a right angle right here. We have a right angle right there. So that means that these are parallel to each other. And again, since we're talking about square lengths for the Pythagorean theorem, we should talk about area here because that'll give us square terms. So let's calculate the area of this shape in 2 ways. First, we'll use that additive property of area. We'll add up the area of each of these triangles. So we have 2 of these blue triangles, which still has an area of 1/2 AB since we're still labeling everything the same. And then this pink triangle, the base and the height are both C, so the area is 1/2 C squared. And then if we just multiply 2 by 1/2, that just gives us 1, so AB plus 1/2 C squared. We can also calculate the area by using the area formula for a trapezoid. That is 1/2 times the height of the trapezoid times the sum of the bases. So the bases are those parallel sides. So here our bases are B and A. So the sum of the bases is A plus B, and the height is this length right here, which is also A plus B. So then using that formula, we get that the area is going to be 1/2 A plus B times A plus B. Multiply everything out. We get 1/2 A squared plus AB plus 1/2 B squared. And again, a shape can only have one area. So if there are 2 different areas calculated, they have to be the same. They have to be equal. So we set that AB plus 1/2 C squared equal to the 1/2 A squared plus AB plus 1/2 B squared. And then it's just simplifying from here. So we have an AB on both sides. We don't need the same thing on both sides of an equation, so we can get rid of it, subtract it off. And then we're left with everything that's multiplied by 1/2. So if we just multiply through by 2, boom, there's our theorem. So the C squared equals A squared plus B squared, and then we're done. And a fun fact about this proof, it was actually developed by President James Garfield. So I believe the story is that back when he was in Congress, it was a particularly boring day on Capitol Hill. So to kill some time, he developed this proof for the Pythagorean theorem. So that's a fun fact about it. And again, I will pause if there are any questions about this one.
Nothing at the moment.
Okay, cool. Feel free to type them like as they come up if you have any questions, and then we can just come to them at the end. But if we're all set on this one, then I'll go ahead to proof number 4.
Okay, I think so.
Okay. So again, this one is a little bit different though, from the first two that we saw. And this one also comes with a little fun fact about who made it. So this proof was developed by Einstein when he was 12 years old. I don't know about you guys, but when I was 12 years old, I was not developing proofs for the Pythagorean theorem. But I guess this is why his name is synonymous with a genius now. So to start off with, this is the picture that we have. Notice that we have 2 right triangles. We have this little yellow one with a hypotenuse of B. We have this medium-sized pink one with a hypotenuse of A. But then we have a 3rd right triangle that's formed by those 2 being put together, and that one has a hypotenuse of C. And so the goal of this one, I'll tell you where we're going with this one. We want to be using similar triangles and get to be using proportions. So a similar triangle is just 2 triangles with different side lengths, but those side lengths are in proportion to each other. So one is twice the size of the other, or 3 times, or 4.5 times, etc. So just some constant times the side lengths. And when we're talking about similar triangles, one way to show that 2 triangles are similar is by showing that all the angles are the same. So here we want to be talking about the angles of these triangles. So when I put in all the labels here, it includes names for the angles. So we already have all the big side lengths named. I'm going to call this little yellow part, the short side of the yellow triangle, I'm going to call that F, and I'm going to call the long leg of the pink triangle E. And then I'm also going to give the angles names like I was saying. So I'm going to call this angle of the pink triangle alpha, this one beta, and then this one up here is delta, and that one's theta. And so, like I was saying before, if all the angles in 2 triangles are the same, then the 2 triangles are similar or in proportion to each other. So our goal right now is to show that instead of 4 different angles, we only have 2 different angles. So we want to show that the theta and the delta are equal to the alpha and the beta. And let's think about what we know about triangles to show that that's true. So the first thing we're going to use is that in a triangle, all the angles add up to 180 degrees. And in a 90-degree triangle, or a right triangle, 90 degrees are already taken care of. So that tells us that the other 2 angles need to add up to 90 degrees. So alpha plus beta, they're going to have to be 90 degrees, and theta plus delta is going to have to be 90 degrees. We also know that this angle right here, this angle right here is 90 degrees. So theta plus alpha, that's also going to have to be 90. And then because this combination yellow-pink triangle is also a right triangle, we know that delta plus beta also have to be 90 degrees. So now we have these 4 equations. They're all equal to 90 degrees, so they're all equal to each other. And we can use that to our advantage. So if we say alpha plus beta equals alpha plus theta, that's true because they're both equal to 90 degrees. Now we have an alpha on either side of this equation, one here, one there. We can subtract it off and we see that beta is actually just theta. We can do it again. We can say that beta plus delta is 90. So alpha plus beta, it's equal to alpha plus beta because that's also 90. There's a beta on both sides, subtract it off. Now we're just left with delta equals alpha. And so that's our first checkpoint. So that's the first thing we wanted to get done. We wanted to show that we really just had 2 different angles instead of 4 different angles. So just relabeling our picture, delta was alpha. So that's right up there, and beta was theta. So we just changed that right there. So since all of the angles in these 2 triangles are the same, that means that the yellow and the pink triangle are similar. But also notice that the angles in the pink and the yellow triangle, oopsies, the angles in the pink and yellow triangle are the same as those in the combination pink and yellow triangle. So the pink triangle is similar to the big one. The yellow triangle is similar to the big one. And that comes in handy because then we can set up little proportional equations. So we can say that the ratio of the hypotenuse of the pink triangle, A, over the hypotenuse of the combo triangle, C, is the same ratio as the long leg of the pink triangle to the long leg of the big triangle, so E over A. And then if we cross multiply, so we're just multiplying this A by that A and C by E, we get A squared equals CE. And we can do the same thing with the yellow triangle. So the ratio of the hypotenuse of the yellow triangle, B, to the hypotenuse of the big triangle, C, is going to be the same as the ratio of the short side of the yellow triangle, F, to the short side of the big triangle, B. And again, we just cross multiply here. So we get B squared equals CF. And what we're looking for is something that's talking about A squared plus B squared. So we have an A squared, we have a B squared. Let's just add them together. If we add the left side of an equation together, we add the right sides as well. So A squared plus B squared equals CE plus CF. So now we're halfway there because the left side of the equation is what we're looking for, the A squared plus B squared. So let's just work with the right side. We have a C in both of these terms, so we can go ahead and factor that out. So if we pull out the C from both of those, then we're left with an E plus F inside these parentheses. But E plus F, that's C, right? Because we just named these E and F, and together they make C. And then just writing that a little bit differently, we have our theorem. And so we're done. Isn't Einstein clever? So again, I'll pause real quick if there are any questions for this one.
None at the moment.
Okay. So then I will move on to the last one. So this one I think is kind of tricky and fun, which are probably things that no one likes to hear about a math thing except someone who likes math. So with this one, what we're starting with is this picture. We have a circle of radius C, and we have this radius coming out and then dropping an altitude from where it hits the circle, and that altitude has a length B, and then we're just kind of connecting it and calling the length that it cuts off A. So this is a little right triangle here. And then this remaining length, well, if the whole thing is C, we take off A. This right here is just C minus A. This one also comes with a little bit of text. So we have this C plus A over B equals B over C minus A. So this isn't something that we know. This is really telling us what our end goal is. So this is what we're trying to show is true. We don't know it's true yet. But the picture has enough information, even though it doesn't look like it, to support that that's true. So let's go through and show why we can use this information. So what I'm going to do is I'm going to just move that text down here so we have a little bit more room to work. I'm also going to do my favorite thing and add a bunch of labels in. And then I am going to also draw some lines in. So I'm going to connect this point we called C to this point we called B, and I'm going to call that line lowercase d. And then I'm going to do the same thing over here. So I'm going to connect point C to point E and call that line lowercase e. So now what we did was we created one big triangle right here. And the important thing to note about this triangle, before we get to that, just more labeling. So we're just gonna give these angles name. So alpha down here, beta is this one going from DCB, it's this angle right there. And then delta is this little angle, theta is that So the important thing to note about the triangle we formed is that it's a right triangle. And the reason it's a right triangle is because an inscribed angle across a diameter is a right angle. So an inscribed angle is just one where the vertex of the angle is on the circle, and then the legs of the angle, they cut off the circle at some point. So here it cuts off a diameter, so it's a 90-degree angle. Again, we're going to be using similar triangles here. So we want to be talking about the angles. And what we want to note is that this big triangle, BDC, that's a right triangle, right? We lost our little right angle indicator when we switched to the side, but this is still a right angle. So this is a right triangle. Angles in a triangle add up to 180. So alpha plus beta have to be 90. If this is 90, this is also 90. So then we have another right triangle. No, sorry, looking at the wrong angle here. Now we're talking about this guy. This is 90 degrees like we just said. So delta plus beta is also going to be 90 degrees. So now we have two things equal to the same thing. So they're equal to each other. We have a beta on both sides, subtract it off. We see that alpha is equal to delta. Now's the time for what I was just saying. So this is a right triangle. So delta and theta have to add up to 90. And then we still have delta and beta are equal to 90. So same thing, set them equal to each other because they're equal to the same thing. We have a delta on both sides. So theta is equal to beta. So again, we really just showed that we only have two different angles here instead of the four different. So it's similar to Einstein's proof that he had. And so when two triangles have the same angle, they're similar. So what we know is that this triangle, BCD, that guy right there, is similar to BEC, that little one right there. Okay. So this is what we're starting with. Triangle BCD is similar to triangle BEC. And then that brings us to that information that we started with, because this is enough to show that that's true. Because the long leg of this big triangle, C plus A, if we make a ratio of that with the long leg of the little triangle B, it's going to be equal to the ratio of the short leg of the big triangle to the short leg of the little one. And then again, we just want to cross multiply. When we do that, we get C plus A times C minus A is equal to B squared. And from here, it's just multiplying and simplifying. So we multiply this out, we get C squared minus CA plus CA minus A squared. These cancel each other out. If we add A squared to both sides, we're done. We get the C squared equals A squared plus B squared. And that's what we were trying to prove. So this one's a little bit tricky because we don't actually use this original triangle other than to draw new triangles and to get the names of the lengths from it. So that one's kind of interesting. If you have questions on this one, that's very understandable. So feel free to ask those. I will pause again and then we can talk about why we want to learn about the Pythagorean theorem.
So Katie, I have a question or clarification just about the inscribed angle. So what you're saying is that anytime there's a triangle where one of the legs is a diameter and then the other point hits the circle, right? That's what that means? Okay.
Yeah, so an inscribed angle, if we have, ooh, that's a very wonky circle. If we have a circle, an inscribed angle is just one where the vertex is on the circle. So that's the vertex. Okay. And this is a very specific case where these 2 points where the angle cuts off the circle happen to be at the diameter. Of the circle.
Okay, so that's why it said any inscribed angle on a diameter, because it wouldn't, if it wasn't on the diameter, then it wouldn't.
Yeah, exactly.
Okay, thank you.
Yeah. Okay. So if we're all set, then I'm
Mhm.
going to go into our next slide.
Okay.
So why study the Pythagorean theorem? So this is probably something that a lot of us thought in high school geometry, but the Pythagorean theorem actually has a lot of applications. So GPS measurements, any construction where you're trying to make right angles, navigation. We wouldn't have been able to land on the moon if we didn't have the Pythagorean theorem. And that's because anytime we're talking about distance in space, the easiest way to find a distance between 2 points is by using straight lines to get there and using the Pythagorean theorem. So that's from an applied standpoint. From a more abstract point, because of the Pythagorean theorem, we were able to get irrational numbers. So an irrational number is just one that can't be written as a fraction. So the square root of 2, for instance, or I, those are both irrational numbers. From the Pythagorean theorem and from working with triangles, the Pythagoreans discovered, but didn't want to acknowledge the existence of irrational numbers. And that's because a lot of ancient mathematicians just didn't like the idea that a number just went on forever and couldn't be written nicely as a fraction. And so this is just a picture of how they came to those irrational numbers. So you start with a right triangle where the legs are of length 1. Then the hypotenuse is going to be square root of 2. And by continuing to build off triangles that have a leg of 1 from that hypotenuse, you can just go through the square root of all counting numbers. So you have the square root of 2, square root of 3, 4, 5, etc. And you can do that for forever and just build a big old spiral. We also have Pythagorean triples, which are just integers that satisfy the Pythagorean theorem. So they're a squared plus b squared equals c squared, just numbers that make that true. 3, 4, and 5, for instance, if you have 3 squared plus 4 squared, that's going to be equal to 5 squared. So that's a Pythagorean triple. These are often studied in number theory. And number theory is just really the study of how numbers relate to each other and the patterns that form when talking about numbers. And it's an example of a Diophantine equation, which is just an equation that has 2 variables. And from Pythagorean triples and from the Pythagorean equation, we have Fermat's last theorem, which is sort of a famous, was for a long time, a famous unsolved problem. And the theorem said that there are no 3 positive integers, a, b, c, that satisfy the equation a to the n plus b to the n equals c to the n for any n equals 2. And that's because if n equals 1, then that's just a plus b equals c. That's true for a lot of things. That's just addition. If n equals 2, that's the Pythagorean equation. We see that that's true. But anything bigger than that, no solution. There aren't going to be any numbers that satisfy that equation. And for a really, really long time, there was only the n equals 4 case was proved. That was done by Fermat in the 1640s. And then up until 1995, when I think he was Scottish, a Scottish mathematician, Andrew Wiles, developed a proof for it. I think he first developed his proof in 1991, if I'm remembering the year correctly, but then there was an error, so he worked at it a little bit more, 4 years of his life, and he was able to come up with a proof for it. And I think that was one of those like $1 million math unsolved problems. They're just like a list of things that have never been solved, but people think they're true. And you can make a lot of money by solving those. So if you're looking for a way to make a lot of money in a very long time, math is the way to do it. So yeah, so that's the end of my talk. Here are a few resources and sources. So what I use for some information in this, the first one is the University of St. Andrews just has this archive of biographies on mathematicians. So if you're really interested in math history and reading about great mathematicians, that's a really good place to start. the University of Illinois at Urbana-Champaign also has a nice little history about the Pythagorean theorem. And then if you just really liked looking at proofs without words, there's a book by Roger B. Nelson that just kind of has a bunch of proofs without words put into one book. There's a PDF of it online. And so if you're looking for a new Sunday morning coffee puzzle, proofs without words, they're a pretty good one. And so yeah, that's the end of my presentation. Thank you for sitting through it. Thank you for being excited about math with me. And yeah, at this point, if there are any questions about anything, feel free to ask.
So first, there is the comment from Phyllis that I use this for machining as well.
There we go.
There you go. But I did have a question about the measuring distances in space.
Yeah.
Because maybe I'm not imagining how this is actually being used for that part. Because I'm thinking,
Yeah.
well, if it's straight line, it's from point A to point B. So where is point C? Why is that there?
Yeah. So if we're in space, the distance equation also has the z-axis to think about. But let's say we're just talking about two-dimensional space, and we're moving in 2 dimensions. So I can draw a little axes here. So if we have, let me change my color. If we have 2 points here, so one over there, we have the line that connects them, the shortest distance right there. But we also have a longer way of going between those 2 points, right? We can go strictly to the left and then, and then strictly up and down. And so now we have our little right triangle. And so the way to find the shortest path between those 2 points is using the Pythagorean theorem.
Okay, so we're assuming that we know kind of where these things exist on a grid.
Yeah.
Okay.
And I mean, that can just be like an arbitrary thing, right? Because you can set up an axis with the center point anywhere. If we wanted to, we can move this over. So then our 0, 0 point is at one of those points.
Okay. I was just trying to imagine like calculating distance from Earth, why you would need multiple points, but I get it now. If it's 2 other points that you're trying to figure out the distance between.
Yeah.
Okay.
Yeah. So like in GPS, there's multiple satellites doing this, and then because I'm not like super well versed in how GPS works, I'll be honest. But with the triangulation of the multiple satellites and them all finding the distance using the Pythagorean theorem.
Cool. Okay. Thank you.
Yeah.
Does anyone else have any questions? Okay, so nothing at the moment, although maybe someone is typing right now. I'm not sure. I do want to say, because I absolutely forgot to mention this to begin with, that Katie is our membership and volunteer coordinator. So you can also find her contact information on the website. If you end up with a question later on, which at least I can just talk to her at work the next day and say, I'm still trying to figure this part out. But if you have questions and you're like me and you kind of mull things over, then you can definitely find her contact information on the website and contact her directly. And so when we say no, but thank you for sharing with us, Katie. And thanks, Katie. I like the presentation. I am one of those people who's tended to kind of assume that math is something that's really challenging. So I really appreciated that you took us step by step, but also that there were multiple ways to get to the solution, so that, help me understand that there's not always one direct line for that.
Yeah, that's kind of the fun thing about when you get farther in math. So when you're talking about higher math, there are less one right answer to get there. So like when you're talking about adding things like 2 plus 3, that's always going to be 5. But when you're talking about proving theorems and things like that, it's a little bit more creative. There's a little bit more wiggle room. The way that I was proving these, going through these proofs, may not be the same way someone else would do it. So there's a little bit of wiggle room with these, which is a fun thing about math.
Yeah, wonderful. Thank you. And so as I said before, those of you who are attending, you're gonna get an email tomorrow asking for feedback, suggestions, things like that. And we hope that you'll join us for future events. We'll be announcing them, and you can look for information about that as we go through this summer. And we'll put this on our website, we'll put them on Facebook and Twitter as well, Instagram, just to let you know what's happening. And we'll, as soon as we have August's details figured out, we'll post those as well. But we want to thank you, and thank you, Katie, for helping us look at math in a different way, and certainly something that, you know, we hear about all the time, but we don't always know where it came from or what it's still used for, aside from when we sat in school and had to, you know, calculate the length of legs of triangles. Okay, so everyone, hope you have a wonderful 4th of July weekend, no matter what it is that you're doing, if you're just staying at home or if you're going someplace socially distant and enjoying some other hopefully nice weather activity. And we'll look forward to seeing you in the future as well.